Did you stop it and then start it again?
Yeah, I'm sorry. I had to make sure it was going the right way.
Right.
It's started again, though.
Wait, I have a question.
Yeah.
Where are you posting all these videos?
On YouTube.
Oh, really?
Kyle set me up with YouTube and Drew with YouTube
Should I
page.
FaceTime Drew right now so he can
I doubt if he feels well to watch Kyle. We'll take care of you, Drew. I'll put this on YouTube. You'll know by then. Okay, the other thing about color I want you to know is this. Transition metal ions almost always have color. There's a few exceptions, but just knowing that transition metal ions have some color, it's not even very important to know what color they are. There's only a few things that you would have to know the color of. One is lead iodide, is yellow. Another one is permanganate. Now, I'm not making a big deal about permanganate because you've used it. What color is permanganate?
Purple.
It's grape juice, yeah, it's purple.
But don't drink it.
What?
Don't drink it.
Yeah, please don't drink it. As much as I love grape juice. And I always think about it when I have
No.
permanganate.
Natural selection. It's okay.
Yeah. I've been hanging around the shelf.
Hey!
So if you are asked about if it gives you calcium carbonate or calcium chromate and asked you which one has a color, then you know the calcium carbonate does not have color because there's no transition metal and the chromate does. So just know that ions containing transition metals almost always have color. If you can remember that, that's fine. Did everybody understand what I just said?
Ions with transition metals always have color.
Transition metal ions have color. Yep. That's good enough. When you go back and look at questions about color, if you just remember those two things, lead iodine and transition metal, you'll be fine. Okay? Sorry, Jessica, you missed it.
We recorded it.
All right. Let's see. Was there anything else about the review? Everybody saw the omitted items, right?
Yeah.
There's a number of things that we had to take out. There was one chapter that we didn't do this year that we've always done in the past. That's about solutions. And there were questions about, they're called colligative properties, like boiling point elevation or freezing point depression. The AP exam doesn't require that anymore, so we have just taken that whole chapter out. There's a few things in that chapter we'll do at the very end of the year, but most of it is gone. So those questions on the review we had to take out. So we've revised the exam. The exam is going to be, I believe, 45 or 46 questions. And you'll have like an hour and 20 minutes to do it. Yes, sir?
Here's really easy.
So you can use a calculator. Yep. I would say that if you have studied, it is easy. There's never a curve. I think I told you that already. We don't ever have to use a curve because the average is always 75 or greater. Usually it's in the 80s. In the 80s, not just 80. So I'm telling you, if you're going to do badly hoping for a curve, then I got bad news for you. Study for it. Have a little study group. Meet a few times. It's going to help a lot. Riaz?
Riyadh.
I would like some real study group. I mean, like,
I've never been in a study group before.
It helps.
It's not.
All right, so this is what we did yesterday. We're talking about strong acids and weak acids. I was talking about strong acids having a single direction arrow in the reaction because they don't come to equilibrium, they just go all the way. There is none of the of the strong acid at the end of the reaction. It's all used up. Not true in a weak acid. A weak acid always comes to equilibrium. In fact, a weak acid only goes a little tiny bit to the right. All weak acids have a K value of less than 1. So they all favor the reactants. If you have a K value greater than 1, you're considered strong. Let's go on to the next page, Spencer. All right, now another thing that I know that you learned in your first chemistry class is what water does just on its own. With no help, no prompting or anything, water ionizes. It releases a hydrogen ion. Does that make it, by definition, acidic? If water releases a hydrogen ion? It does, yeah. But it also releases a hydroxide ion when it breaks apart. Does that make it, by definition, a base?
No.
Yes.
No.
Yeah.
Releases a
Yes.
hydroxide ion.
No.
Yes.
No, it's a, guys, that's only if it's Bronson Lowry, isn't it?
No, it's not Bronson.
Wait.
No.
If something increases the hydroxide concentration, then make it a base?
Yes. Not necessarily.
Well, this is an equilibrium. Bronstein-Lowry says if the hydroxide can be, well, the water is not acting as a hydrogen acceptor. That's true.
Yeah.
But as an Arrhenius base, it is giving off hydroxide. So when you consider water to be acidic, is water an acid in general? No, because it's making hydrogen ions and hydroxide ions in the same concentration. It does not make it acidic. The pH of pure water is 7. It's not less than 7. It is 7. So yeah, even though water is giving off a hydrogen, it's not considered acidic because it's giving off a hydroxide too. It comes to equilibrium. It only goes to the right a tiny little bit and then stops. So that the K that we use for this thing, and notice that water on the left side is a liquid. It does not go into the K expression. Just the two aqueous things do. The liquids and solids in equilibrium values, you just give a 1 to. It's the number 1. So it would be that times that over 1. We just leave the 1 on. And you see that it's a very small number for K. It's 10 to the negative 14th power. So it heavily favors the left side. I've had people, both hours today, ask, does the K for water change with temperature? If you heat water up, does it change the K? Yeah. I believe this is an endothermic process, so the heat would be on the left. So the K does increase a little bit as you increase the temperature. Now, what's nice is you're never going to have to worry about water changing temperature, what the new K value is. Everything in this chapter, and the next chapter, and the following chapter are all at 25 degrees. Everything's at 25. So we're not using any temperature effect at all now for a while. Let's move down just a little bit, Spencer. Down into the weak acid. Go, 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 kill it until we have another K value. Keep going. Okay, stop. That's good. When you have a weak acid, you can find the K for a weak acid. You write out the chemical equation for the acid releasing its hydrogen. So this is an example of a weak acid, HNO2. It gives off a hydrogen ion, and then NO2 is also produced. The K expression for this, those are aqueous, and this is aqueous, so it's products over reactants. There they are. This value will also be less than 1. It's not going to be as small as that, but it's small. We identify the NO2 negative 1. We give it a name. We're going to rename it, I guess, but it's got like a label or a title. Anybody remember what that's called? It starts with a C.
Clock.
Yes. Jessica. The conjugate base. Conjugate base.
Clock.
We're getting there.
I'm not confused.
It was a joke.
Really?
I'm sure it was.
You know that.
So yeah, this is our acid. This is considered the conjugate base. Why would we consider that the conjugate base? What do you mean by base?
Oh,
Yes.
basically,
Basically, you've already said the answer.
Basically.
No, go ahead.
okay. So basically, it comes from the acid that turns into the base.
How does it turn into a base? Is that what base
Because it
is?
loses
It
the
broke up and loses the hydrogen.
Yeah. But remember, this is a reversible reaction.
Yeah.
It could go that way.
Yeah.
So as it goes that way, what's that doing?
That becomes the
Acidifying.
base.
Yeah, it's accepting a hydrogen in that direction, which makes it a base. Yep. Is this going to be basic, like if I just put it into water? Can it take a hydrogen from a water molecule?
Sure.
It can. Yep. It's not really strong as a base, but it can. So, I was just going to do that, but I got Spencer to do that for me. Let's move down another one, Spencer.
Wait, does it still not work?
Yeah.
And it still doesn't work. Perfect. Now, NO2 negative 1, when it acts like a base, you put it into water like this, and it can take a hydrogen from water, and that's what makes it a base. And what do you get? You get HNO2. It's what you started with up here. So this is the conjugate acid of that base. Yeah? The conjugate pairs. And then the other product that's formed is the water molecule. The water was giving its hydrogen away, so it's left as a hydroxide ion. So this thing in water will increase the hydroxide concentration because some of the waters are losing the hydrogen. So the Kb for that base, with a little b means base, it would be that times that, those are both aqueous, divided by just the NO2 because the water, the other reactant, is liquid.
So in this, water is acting as an acid?
Yes, the water's acting like an acid. Yep. I'm going to rewrite these. I'm really looking forward to when I can write on the smartboard again.
You could just use normal markers.
You just write on it.
I understand the markers don't erase very well on there.
No.
Have you tried?
No, I haven't.
Put saran wrap over it.
Oh, saran wrap.
Yeah.
Oh, that's a good idea.
Yeah.
Dang.
Almost as good as Felix's whiteboard.
Felix had the classic. I love that.
It was very smart.
It was a white.
I'm not putting physical states in again, but I just want to put that. Now, we have this reaction, which is HNO2 acting as an acid, so we gave a K value for that called a Ka. This is the conjugate base acting like a base. We give that equilibrium K a Kb. Now, here's a good thing. When you add these two together, add the two reactions together, you see some things cancel out. Right.
Oh.
And what does that leave us with? Leaves us with water yields hydrogen plus hydroxide. Now here's the really good thing. The K for this thing, now that's going to be Kw again.
KB minus.
What do you do with the K's when you add two equations together?
Add them together.
You multiply them. Oh, yeah. So that means that when I've added these two together, I get the Kw reaction back. So the Kw is equal to what? Ka times Kb. So anytime you know the Ka of an acid, you can always find the Kb of its conjugate base.
If you know what the K. Oh wait, the K.
You always know
Kw is
Kw, it's a constant.
Oh,
It's a constant.
that's actually really cool.
It is cool. And you'll use this relationship quite a bit. This chapter, and especially in the next chapter. The next chapter is about buffers. It's where you have an acid mixed with its conjugate base. And we'll have to know Kas of acids and Kbs of bases a lot. Pretty much in every problem.
Is there a way to like conjugate Ka, or do you just need a table?
You have to have a table. There's no way to just theoretically know what Ka values are. Yep. How do you like that? Good? All right, Spencer, let's move on. Now, this we did yesterday. This is what your first reading quiz in this chapter was about: strength of acids as a result of their structure. I'm not giving you time to write this down. We did this for enough of the hour yesterday. I don't want to take more time today. Just remember this. When your H is attached to something that's very high in electronegativity or electropositivity, according to Devin, the electrons are pulled away from the hydrogen, make it easy for it to leave. So H attached to a very electronegative thing, like a halogen, makes it a strong acid. What if H is attached to a polyatomic ion?
More O's.
The more O's, the stronger. You got it.
So as a universal rule, basically just more O's is stronger?
Yes.
Or have a polar bond?
Yeah, the more polar or the more O's. Yep. That's what I want you to know. As I said before, almost every year, there's a question about that on the AP exam. So just be on the lookout. Yeah.
When we're talking about polar bonds, what does that refer to again?
We're going to get into polar bonds later on in the year, but hydrogen is far on the left of the periodic table. It's not good at hanging on and pulling electrons. So the farther to the right you go. Fluorine is the highest in electronegativity.
Oh, okay.
And down and left, they decrease in electronegativity. Like francium would be the lowest electronegativity.
Like if you compare like oxygen and chlor.
Yeah, and I had that too. How do you compare them? You won't really need to compare them. If H is attached to anything that's right and up, it's going to be a pretty good acid.
Okay.
Yeah. Water is not a good acid. It has to do with the hydrogen bonding in water. The oxygen does not let the hydrogen leave because of the hydrogen bonding. And we'll talk about that too later in the year.
Isn't it because like oxygen's okay with like two bonds?
You could
Yes,
probably
that's exactly what it is. Yeah.
Oh, was I supposed to lower this?
No, I didn't want you.
Just kidding.
Because I don't want people to just copy that down. We're not giving you time. Well, let's move on.
Wait, can I see what it says?
Don't we just see it?
Yeah, you can see it.